Welcome to a new Alientech video. After seeing how the mass flow metering strategy works, today we are going to see how the new generation ECUs have introduced the torque calculation strategy. Let's not waste any more time and get started right away. As we saw for the fuel control strategy, the external torque demand is performed by the driver via the accelerator pedal, based on the pedal pressure expressed as a percentage. The ECU will not perceive a demand for fuel, but a greater or lesser demand for torque. The torque calculation allows an optimal exchange of data between the engine control unit and that of the other modules connected to the vehicle's internal network, such as the gearbox and body computer, between the engine control unit and the devices that can be connected to the OBD2 diagnostic socket, and finally, with vehicle stability and traction control systems such as ESP, ASR, and ABS, for example. Why was the torque calculation chosen instead of the power calculation? ECU developers chose torque rather than power, mainly because knowing the pressure, volume, and type of engine, it is easy to calculate, even without specific sensors or measuring equipment. As for the power, rather, it would be necessary to install an eddy current electrical motor directly on the motor shaft in order to be able to measure the electrical power generated by the motor shaft. This solution, in addition to an excessive cost, requires rather complex calibrations. A different option is that a formula would need to be introduced by measuring the RPM sensor placed on the phonic wheel, but this would decrease the precision of the calculation due to its accuracy and aging characteristics of the sensor. Not to mention that if it were damaged, the entire strategy would cease to function. This is why the manufacturers have opted for the torque calculation strategy. Let's go into more detail by taking a look at and analyzing the structure of a system based on torque calculation. Look at the diagram starting from the left. It is immediately understandable that the three quantities that determine the engine torque are the ideal torque demand that the driver requires by acting on the accelerator pedal, the ideal torque demand that the cruise control system adjusts to keep cruising speed constant when it is active and when the driver does not press the accelerator pedal, the ideal torque value lost due to the management of accessories operating at a specific moment. In fact, two of the three parameters that act in the torque coordination process depend on an action by the driver, while the third, less important but still relevant, depends on the accessories that are active and that operate by decreasing engine performance. In the block called the internal torque request, the control unit checks whether the torque request has been made via the accelerator pedal or with the cruise control, with either value sent expressed in Newton meters. This value can be positive or negative. When positive, we have the engine torque desired by the driver and ideally delivered by the engine, such as the torque requested through the accelerator pedal. When negative, on the other hand, the desired engine torque will be decreased to regain stability, such as in dangerous driving conditions. If the vehicle stability control starts automatically, it will also provide values expressed in Newton meters to the internal torque request block, but instead of positive, they will have negative values. The output value, in both cases, is subsequently sent to two different blocks: power management and powertrain control. Power management has the task of comparing whether the torque required to keep some accessory systems running, such as the air conditioning compressor, is higher or lower than desired. The kinematic chain control, or powertrain control, has the task of carrying out the first check between the torque required through the accelerator pedal, or the cruise control, the former coming from the power management block, and the latter linked to the selected gear, coming from the transmission block. The result is to obtain a desired torque value that does not present sudden or slow variations related to the accelerator pedal or the cruise control system. So, for all intents and purposes, the final torque value that the ECU needs to calculate depends on the output from the kinematic chain control block, minus the lost torque value linked to the power management. The latter is an experimental data calculated during the design phase, usually dependent on two factors: engine speed and engine coolant temperature in degrees centigrade. At this point, if the torque value is lower than that contained in the engine protection block, the torque is converted into fuel quantity, transforming Newton meters into milligrams of fuel per cycle or into volume of fuel per cycle. Pay close attention now. It is at this point of the strategy that the so-called torque limitation maps intervene. The same block could contain fuel quantity values which represent the limitation of the injected quantity. These limitations can be linked to physical limits of the engine or its components, such as the maximum flow rate of the injectors, or to limits set by the manufacturers. The torque-to-fuel conversion block also has a connection with the engine ignition block. Torque required during starting, which includes one or more maps expressed in Newton meters, which represent the required torque and, consequently, the fuel to be injected to start the engine. Continuing in the analysis of the diagram to the right, we find two other blocks. The injection system, dependent on the injection technology that is used to power the engine, i.e. the injection pump, injector pump, or common rail. The fuel balance control. Balance is related to four factors, which can be individually controlled or not, depending on the technology. We then have the injection phase, the fuel pressure, the injection time, and the injected quantity. Finally, the air system block is linked both to the carburation and to the prevention and control of emissions generated by the engine. As we have seen from the previous videos, the two main factors involved in the combustion process of a diesel engine are fuel and air. It is now clear that fuel depends primarily on the driver's demand for performance, and the air will only serve to completely burn all the fuel injected. With this last block, we arrive at the end of the structure of a system based on torque calculation. Let's make a quick summary of what we have seen to make sure we memorize the elements of the scheme. 1. It all starts with demand imposed from the outside, which, as we have seen, can be required by setting the cruise control or by the driver pressing the accelerator pedal. 2. Then the request goes to the internal torque request block. The control unit communicates with the ESP control unit to understand if the wheels of the vehicle are slipping, or if everything is working correctly, and if necessary, it acts to bring all the wheels back to the same speed and thus avoid the slipping. 3. The engine control unit now communicates with the control unit that manages the accessory powers to give sufficient torque to the accessories such as the air conditioning, the power steering, the alternator if it charges the battery, or other accessories. 4. Afterwards, the properly adjusted torque is transmitted to the control block of the kinematic chain and, consequently, manages the maximum possible torque for the gearbox through the gearbox control unit, also called the TCU. 5. The ECU calculates the torque lost due to friction, the torque needed to maintain at idle the engine RPM, and checks if there are some torque limiters that can limit the maximum torque. 6. After this check, all the calculated torque is generated through the actuators present in the engine system, such as injection and air control. We've talked about the blocks. We also find some abbreviations placed near the directional arrows. These are the abbreviations used within the demos, a document containing the information of everything present in an original file, inside the ECU. If, for example, we wanted to find the torque request maps using the accelerator pedal, the code is ACCPED_TRQDES, which stands for Accelerator Pedal Torque Desired. Or to find the torque request map through the cruise control, the code is CRCTL_TRQDES, which stands for Cruise Control Desired Torque. It is important to remember that the vehicle speed limiter can be external or internal to the original ECU file. For example, Iveco sells its daily with different configurations, such as closed configuration, high roof, or open body. So, the manufacturer, together with Bosch, defines that the speed limitation is contained within the EEPROM memory, in order to be able, based on the vehicle setup, to vary the limitation using the official diagnostic tester. In the video concerning the operating strategy, which considered only the injected fuel, we saw that the torque calculation strategy uses multiple maps to control the outputs of the actuators. Let's explore them together. Starting from the engine torque category, let's analyze the torque request maps. The map in question is expressed in Newton meters, as a function of the engine speed and on the basis of the pressure in percentage that the driver exerts on the accelerator pedal. By modifying this map, we can change the sensitivity of the accelerator pedal and, by increasing the values inside it, require more torque. Once this is done, it is necessary to check if the original file contains some limiters with which the manufacturer limits the engine torque. To do this, we must go and see the maximum torque limiter maps. This map is also expressed in Newton meters as a function of the atmospheric pressure and engine speed. In this map, used as an example, we immediately see that the highest values reach 350 Newton meters, therefore higher than those declared in the torque request. From this, we understand that the manufacturer often creates higher limitations at the start compared to the values that the vehicle can originally reach. In case our modification expects to exceed the values imposed by a specific limiter, it is necessary to increase the original limitation. Moving on to analyze another torque limiter. We find that it too is expressed in Newton meters and has no reference axis. In the torque request map, seen previously, and used as an example, we can request up to 339.9 Newton meters by pressing the accelerator pedal to 100%. But in this case, the torque will be limited to 320 Newton meters, because the engine control unit reads as reference the lower limitation value. It is important to remember to check all torque limitations, such as the maximum torque as a function of a specific gear, or other torque limiters, to see if torque can be limited by additional maps. At this point, after having increased the sensitivity of the accelerator pedal and checked the various limiters, we must check the amount of fuel injected and understand if we can actually generate the required torque. To do this, we need to move to another category of maps, the injection system, and analyze the fuel quantity injected map. This time, the map is a function of the engine revolutions and Newton meters, and we find values expressed in cubic millimeters of fuel injected per engine cycle. If we have increased the torque request map beyond the maximum torque that this map can handle, we should also increase this fuel quantity injected map in order to inject the fuel needed to generate the new torque value. The fuel to be injected also has its own respective fuel quantity limiter maps. Let's go take a look at one. As a function of the engine revolutions and the pressure inside our intake manifold, the limiter expresses the cubic millimeters of fuel injected per engine cycle. These maps serve, in fact, to limit the amount of fuel being injected, which, consequently, indirectly limits the engine torque and smoke. Now, let's instead check the injector opening time. Look at the injection time map to perform the operation. This map works as a function of the rail pressure and the cubic millimeters of fuel injected per engine cycle, while the values of the map are expressed in microseconds, which determine the time that the injector must remain open to inject all the calculated diesel fuel. Therefore, the higher the values, the greater the amount of fuel injected, but with low rail pressure. The lowest values, on the other hand, are found with a low amount of injected fuel and very high rail pressure. Well, once we have verified that the injection time is calibrated to inject all the fuel required, we need to change the injection phase. Let's take a look at the map in detail. The map is a function of the engine revolutions and the cubic millimeters of fuel injected per engine cycle. The values in the map are expressed in degrees before the piston reaches the top dead center. This serves to manage the moment at which the diesel must be injected into the cylinders. Furthermore, Remember that these maps can be represented based on a specific condition of the ECU. For example, there is a group of maps that will be used in a regeneration mode, others during normal operation, or some in a protection mode. Let's analyze another very important map, the rail pressure map. It is important to completely understand how these types of maps work, as they can greatly increase the performance of a vehicle. But in an old car, rather, these could damage the injectors and maybe even the high-pressure fuel pump. This map is used by the control unit to determine the pressure expressed in bars, with which the fuel is injected into the combustion chamber as a function of the engine revolutions and the cubic millimeters of fuel injected per engine cycle. When the number of revolutions is very low, let's assume at idle, the amount of fuel injected will be very low, and consequently, so will the rail pressure. On the other hand, when we increase the number of revolutions, RPMs, the high-pressure pump connected to the engine service belt will be able to generate a higher injection pressure, and the control unit will be able to manage a greater quantity of injected fuel. Remember that the increase in rail pressure could also decrease instantaneous consumption due to greater efficiency caused by the greater atomization of diesel fuel inside the cylinders, also causing increased injector wear. In this map, we also find the relative limiters that can limit the pressure of the rail. The rail pressure limiter maps can generally be found according to the amount of fuel injected or the temperature of the fuel injected. However, the operation remains unchanged. Let's take a look at one in detail. This map represents, as a function of the engine revolutions and the cubic millimeters of fuel injected per engine cycle, the limitation values for the rail expressed in pressure. Finally, let's take a look at the last category of turbo, specifically the turbo pressure map. Within this map, we find absolute pressure values inside the intake manifold expressed in hectopascals, as a function of engine revolutions and cubic millimeters of fuel injected per engine cycle. These maps set the target pressure that the turbocharger will have to reach. So by increasing the values of this map, we require more air in order to burn all the fuel we are going to inject. And finally, here we are at the last limiter, called the turbo pressure limiter. These maps are concerned with limiting the maximum pressure that the turbo can reach, as a function of the engine revolutions and the cubic millimeters of fuel injected per engine cycle. The values in the map are expressed in absolute pressure inside the intake manifold. Attention! It is often possible to find this map expressed with a single point value. Usually, this represents the maximum value that the map sensor can measure. Once the engine control unit has properly defined the outputs for the actuators, it checks for any corrections to be applied to the quantity of fuel to be injected, according to various parameters measured by the sensors, such as this map, expressed as a percentage of correction as a function of the coolant temperature in degrees centigrade and the vehicle speed kilometers per hour. Let's read this map together. With the values at 100% means all the fuel injected and therefore without corrections. Vice versa with values below 100%. There are many factors that can determine a correction of the fuel to be injected, but all are closely linked to limit conditions measured by the various sensors present in the various last-generation diesel systems. We are almost at the end of this appointment, but first, let's conclude by analyzing the advantages and disadvantages of this strategy. While on the one hand, the injection strategy based on the calculation of the engine torque has allowed many tuners, even inexperienced ones, to take their first steps into the tuning world, on the other hand, it has allowed ECU developers to introduce even more control maps and limiters. Additionally, some engine torque maps have been associated with software monitoring strategies and fault codes, or DTCs. This represented a further obstacle for tuners, since the ways to bypass or deactivate the monitoring are different, not only according to the manufacturer of the control unit, but also according to the make or manufacturer of the vehicle. This is due to the fact that they are sometimes associated with manufacturer-specific fault codes. We also remind you that, unlike the mass flow metering strategy, which continues to base its operation on the basis of engine RPMs and load, the strategy based on engine torque control can independently use only the MAF sensor or the MAP sensor. As a matter of precision and, above all, to keep emissions as low as possible, many of today's vehicles are equipped with both sensors. In the following video, we will see an evolution of this system, in which the manufacturers have implemented a control to check whether the ECU internally calculated engine torque is correct or not. This is called torque monitoring. Don't miss it. I'm waiting for you.